think we're recording. Oh, yeah, there we go. All right. All right, guys, I will begin with a word of prayer. Ahem. Hem. Hem. It's a new noise. Yeah. I will pray. Dear Father, we thank you for this day. I thank you for these students. I just ask that you bless our work today. Help us to understand a little bit more about your creation together, Lord, as we study, Lord. In your name I pray. Amen. So you guys have questions? Questions? If there aren't questions, I'll go on, and we can have questions later. It's up to you guys. Yep. Number 3 on page 164. I will try. So here's the question. How much work did the movers do horizontally, pushing a 46-kilogram crate 10.3 meters across a rough floor without acceleration? So we got a crate, and it goes a distance of 10.3 meters, right? And it says the coefficient of friction is 0.5, and it's 46 kilogram crate, right? And no acceleration. What's that mean? Why is that important? What if there was acceleration? What would that change? It would change, well, yeah, it would change the force that was applied, that's true. But it would also mean that there's a change in kinetic energy, right? So if they sped up the box, then the work that was required to move the box from one point to another would include two terms. You know, the energy it took to build up the kinetic energy, but also the energy that they're losing to the friction, yeah? So here, there's no buildup of kinetic energy. It's still just barely moving along, all right? And so the work done by the movers is just equal to the friction force times the distance. Because, and to be more clear, so here's the force of the movers is like this, right? What direction is the friction force going? I heard opposite direction, right? So if we're interested in the sign of the work done by the movers, is it positive or negative? So the work done by the movers on the box is the negative work because it's opposite the direction of motion. Now, it depends on the wording of the question whether or not we're supposed to give a negative answer or a positive answer here. A lot of times they'll ask you for the magnitude of the work done, so you don't have to worry about it because magnitude is positive. What I've written down right here at the moment is the magnitude of the, well, it depends. Let's just calculate the magnitude of the work done just to not worry about that minus. Now, so what's the force of friction? It's mu times the normal force, right? And so what's the normal force here? Yeah, it's exactly, it's just the weight. So this is 0.5 times my mass, which is 46 kilograms. And G is 9.8 meters per second squared. And the distance is 10.3 meters. Goodness, I feel like if I ask this on a test, everybody get it right for the wrong reasons. Because you guys would just take the numbers and multiply them. Be like, answer. No one understanding a bit of what they just did. Right? Just blindly multiplying numbers, hoping something sticks, right? So you know how I fixed that to see if you guys understand or don't? It's pretty simple. I just add an extra piece of information, which is extraneous. That's not mean. I'm just making sure you know physics. No? So whatever that works out to, does that answer your question? I think it does. Yes? No? Okay. Next question? Yep. Number 29 on page 165. Here we have a 1.6 meter tall person lift a 1.65 kilogram book off the ground. So it's 2.2. What? Oh, I was reading number 30. Sorry. I'll do that. Let's try that again. A 66.5 kilogram hiker. Number 29. Page 165. 66.5 kilogram hiker starts at elevation of 1,270 meters and climbs to 2,660 meters, right? And then questions A, the hiker's, what's the change in potential energy for the hiker, right? What's the change in potential energy for the hiker? What's the minimum work required? Of the hiker, right? And C, would the actual work be greater than this? All right, so I think a little picture is helpful here. So probably don't even need it, but I'll just draw it anyway. So here we go. So down here, 1,270 meters equals h. And up here at the end point, I'm not sure why they're wearing a top hat while hiking, but don't question it. And over here, so this is H0, HF, the final height is 2,660 meters, right? So what's the change in potential energy? We can answer that, right? The change in potential energy is equal to potential energy final minus potential energy. My board is starting to come undone. Oh no. I think I'm going to need to bring Dr. Sprano back over here and remount the board. Maybe I'll bring a level from home this time. Yes. Yeah, it's bothering you guys? Yes. He's probably keeping you awake. No? No? It's just unsettling. Are you analytical types? All right, very good. So the potential energy due to gravity close to the surface of the Earth, mgHf minus mgh naught. So of course we can factor out mg. We got what? Mg, the change in the height actually, right? And so the change in potential energy here would be, oh, there's my mass, 66.5 kilograms. We're assuming that the hiker does not lose weight while hiking. All right. That would be nice. Yeah, it doesn't happen that fast, does it? All right, 9.8 meters per second squared. Maybe they ate one of those energy bars and gained a kilogram. I don't know. Let's see here. Where are we? Oh, yeah, 2660 minus 1270, like so. And we just got to crunch those numbers, and that will tell us what the change in potential energy is. So, you know, this change in potential energy, how is it happening? It's happening because the hiker is exerting force through their legs to go up the mountain, right? And where's that force coming from? It's coming from, you know, chemical energy that's converted from food and so forth and so on, right? So it's whoa. Yowzers. Did you guys get that?
Yeah.
645,183?
I got the book says 9.06 because I kept getting the 6. I got book says 6.
All right, let me try again. Oh, I know what I did. I did 2260. It's 2660. My bad. I have 905,863. 905,863. What? It's energy. What are the units? The units are joules, also known as Newton meters. Now that, in a better way to write that is 9.05, let's say 9, times 10 to the what joules? Yeah, 10 to the 5th joules. Or if you want to be silly, 0.9059 megajoules. I like this one though. Any of the last 3 answers would be counted as correct on my test. All right? What's the minimum work required of the hiker? Well, where's this change in potential energy coming from? It's coming from the work done by the hiker, right? That is the minimum work required of the hiker right there. The reason it's minimum is if the hiker started from rest, right? And then at the top of the hill, the hiker has any kind of speed going right here. Like suppose he's still booking it like 2 meters per second. You know, if he's moving 2 meters per second, then he has energy, kinetic energy, in addition to the potential energy, right? So that's one thing. If he has any kinetic energy at the end, then he's done more work than just the change in potential energy. But what's the other more interesting thing? Which takes more work? If you climb like this over 10 meters, right? And suppose this is 10 meters up. Well, let's say let's make it 1 meter. That's a bad picture. Try that again. There, 3 meters. Suppose you climb a 3-meter ramp 10 meters over like that, right? Think about your change of potential energy. What if you instead walked up an incline like this, and my picture's not to scale, but suppose this is 10 kilometers and this is 3 meters. The change in potential energy for both of these paths is the same. It's the mass times the gravity times 3 meters from start to end. What is going to take you more work? I mean, in terms of an actual physical situation, not these hypothetical frictionless physics problems we sometimes talk about. The 10 kilometer, right? Because you had to walk almost 10 kilometers, right? That takes work, right? Because why? You're working against friction, there's air resistance, there's all kinds of stuff, right? So all like the friction, the air resistance, all of the things which have nothing to do with gravitational potential energy, still you have to overcome as you're hiking up a trail, right? I mean, if the trail has a certain vertical displacement, there's always the change in potential energy you have to overcome, but the rest of the trail, the length of it, will change how much work you have to do as you go along the trail. Just the process of walking, you know, it's not there's lots of energy wasted, right? Your shoes make noise, that's energy being lost. Your feet heat up inside your shoes, that's energy being lost. I mean, there's all kinds of ways you're losing energy. All right, I shut up. Next question, yep. 35, same page? The spring, the vertical spring? Okay. Excellent. Ah. Yeah? Yeah. Oh, that was what I was talking about the last 2 minutes. The minimum work required of the hiker is exactly that. The answer to A and B is the same. A is the answer to B. Okay. And then C, the actual work, yes, it would be greater because there's all kinds of friction forces and things like that. You might be speeding up as well. That's the answer to C. Was it 35? Okay, number 35. Oh, man. Number 35. Ah, this marker has not long to live. You have a spring with spring constant K equals to,
Same page.
yeah, page 165. Spring constant K equals 83 newtons per meter, the so-called stiffness of the spring. It hangs vertically next to a ruler. All right. And the end of the spring is next to the 15 centimeter mark of the ruler. All right. I'm trying to think if the ruler, it's not clear to me if the ruler is attached. Where's the top of where's the start of the ruler? I mean, my question is this the 15 centimeter mark?
Yeah, that's what
Or is this the 15 centimeter mark? Or does it matter? The spring is next to the, all right, well, let's just think about it this one to start with. Like this one, rather. All right? There's a spring. 2.5 kilogram mass is now attached to the end of the spring, and the mass is allowed to fall. Where will the end of the spring line up with the ruler marks when the mass is at its lowest position? I think it's probably this one they want us to think about, but so, you know, we take this this mass, what's the mass? Yeah, 2.5 kilograms. Okay. Listen, we're going to start with the right diagram, and we'll decide at the end of our analysis if the left diagram is even possible. All right? It may not even make sense. So what's the end? We start from rest, right? There's two situations here. There's this one, and then the spring is stretched out, right, to its final x. Maybe I should just say, let's use y since it's vertical, yeah. So the final y is like that, right? So what's the energy situation to start with? What are the energies involved here? We have kinetic energy, we have gravitational energy, and we have spring potential energy. There's three, like the total energy here at any time, energy would be equal to potential energy, gravitational rather, so much writing, plus potential energy of the spring, plus the kinetic energy of the mass, yeah? So this is a conservative process. At any point, the net energy is conserved. It stays constant, right? Actually, both of the situations that were given have no kinetic energy, so that's even not, in some sense, not interesting to this problem. The kinetic energy, when we let it go from rest, is 0, and the kinetic energy at the very end, when the spring is entirely stretched out, is also 0. So we've got no kinetic energy entering the story. So the initial potential energy, let's see here. So E0 would be the initial potential energy of the spring, right? Plus the potential energy of gravity. I'm just repeating myself. Let me stop that. So what is the initial potential energy? 1/2 K times 0 squared, right? Because the spring not stretched, right? It's at its equilibrium if it's just hanging there. How about the gravitational? Now, so the question is, where do you want to set the gravitational potential energy to be 0? You want the gravitational potential energy to be 0 at the top of the ruler.
Where the 15 centimeters is that?
Even the gentleman with the hat says no to that. And we know he's a scoundrel, so like he's not have my best interest in mind. What's that?
No, wait,
At the bottom? So I think, yeah, let's make this h equals to 0. How about that? Does that sound reasonable? Why not? You can't be wrong here. It's just it's a question of preference. If we do make that h equals to 0, there is originally some gravitational potential energy. How much is there? Now the question is, what kind of ruler are we using? Right? Is it, yeah, let's say it's a meter stick, right? That seems reasonable. If it's got 15 centimeters on it, it's probably a meter stick. Anyway, let's say it's a meter stick. If it is a meter stick, what's the initial potential energy here? I mean, what's the initial, this is h equals to what? 100 minus 15, 85, right? So plus mg, let's see here. You know what, let's just call this, well, fine, 85. Oh, but let's do, yes, indeed, let's do 0.85. 0.85 meters, right? That's the, so there you go. That's the initial potential energy of the spring. Now, which mass goes there? Of course, the 2.5 kilograms, right? That's the initial potential energy. And how about what's the final situation here? Well, in the end, we've got what? We've got, we have 1/2 k, and, well, then the question is, you know, this is the distance that the spring has stretched, right? So maybe we should call that something. I think calling that YF is probably a bad idea. I'm going to back off my YF label. I'm starting to not like it. What do you think we should call the black distance I just illustrated there? It is the x for the spring force, right? You want to call it x? We could call it x. Let's call it x. Why not? I'm not against that. So 1/2 kx squared. That's the spring potential energy, right? And there's still gravitational energy. How much gravitational energy do we have at this point? Plus mg what? What goes here? What's h? You gotta now. You see, now we gotta think a little bit here, right? So this down here is hf. So what we have is we have the final h plus x plus 0.15 meters. This is equal to what? The length of the meter stick, right? So this is the relation between the distance that the spring stretches, the distance from the base of the meter stick. So we can solve that. What is HF actually equal to? 0.85. Yeah, okay, is it I heard 0.85 minus x, is it? That's 0.85 meters, of course. Feeling guilty about not putting my meters in. There we go. And that's equal to what? That's equal to the initial energy, because energy is conserved here. So that's equal to mg times 0.85 meters. So you see the 0.85s cancel, right? And what are you left with? You're left with 1/2 kx squared equals what? mgx. Which is a way, maybe, so what I'm trying to get at here is maybe this is a better way to think about it. What's a better way to think about this problem, perhaps? Maybe we should think about the change in potential energy. Maybe that's a good way to think about it. The change in gravitational potential energy is equal to the change in what? The spring's potential energy in this situation because there's no kinetic energy before or after, right? So these have to be matched. And that's all this equation says. It says that the potential energy gained by the spring, right, is what? It's equal to the potential energy lost gravitationally for gravity, yeah? So it's just this balance of these two things. And then, of course, we can solve this, right? We don't know what x is, but we can figure it out. I mean, is x equal to 0? Could x be 0? No, it's pretty clear that x equals 0 is an unphysical solution. So we can divide by x without losing anything. And what's that give us? 1/2 kx equals to mg, which then gives me x is equal to 2mg divided by k, and I know all those things. So that's 2 times 2.5 kilograms times 9.8 meters per second squared divided by my spring constant of 83 newtons divided by meters. And so that should get me the answer. So, of course, I could have just told you, oh, you just set 1/2 kx squared equal to mgx at the start of it, right? But I think it's important to reason through it. It's energy conservation. You want to think about conserving energy as a way to solve this problem. Because if you understand it from that perspective, you can solve not just this problem, but other related problems to this. Let's see here. So 2 times 2.5, 9.8 divided by 83. I get 0.5904 meters, aka 59.04 centimeters, yeah?
Okay, because it says like where it is on the board. So then I guess
Now that, right, now we have to add 15 to that, right?
because after it, like,
Yeah, so 74.04 would be the answer, given the wording of the problem. 74.04 centimeters. And it, you know, it wouldn't have mattered, right? It wouldn't have mattered if we were in this situation, right? And the spring had looked like this, then what would have happened? After you released the mass, it would have gone and, you know, final position down here, wherever that was. And this would have been 74, you know, that would have been 59.04 below the 15 centimeter mark. It doesn't really matter which end is up on the ruler, right? So, well, I mean, or it could be, I guess the other perspective is that this wouldn't make sense. I mean, I should say, because that would actually be what? 15 minus, excuse me, this would be the what? I'm an idiot. That would not make sense, would it? Because the ruler only goes to where? Like there, right? So you're below the ruler. So it can't be that it's starting 15 from this and then dropping 59. That would be, you know, 45 centimeters below where the ruler is. This would not make sense for the problem. So it has to be that one. When I give problems like this, if you're in doubt, you ask me, and I will draw you a picture, okay? It's not like on my list of things to test you on. Here's a problem with 2 possible interpretations. Let students work both hypothetically and then choose from these which one it should be. That's not how I operate in here. I mean, if we had physics majors, that would be my MO, but we do not have physics majors because we do not have a physics major. So there you go. Oh, you maybe have other questions, yeah? Does that get that one? Okay. Going to erase the evidence here. Oh, there it is. So next. Yeah. 71 on page 167. All right. Bleh, I can't say words. A cyclist coasts down a 6-degree hill at a steady speed of 4 meters per second. All right, I believe that means that this is 6 degrees, right? At least that's my interpretation. And I'm not very good at drawing bicycles, but here's my, there we go. There we go. Oh yeah, 4 meters per second. And what are we asked? Steady speed of 4 meters per second. Assuming a total mass of 75 kilograms, I guess that's the cyclist and the bike together. What must the cyclist's power output be to climb the hill at the same speed? What? There's a naive way to answer this question, and there's a sophisticated way to answer the question. The naive way is to ignore what we're told at the beginning and to just answer the question over here, completely ignoring friction, right? If we just ignore friction, to find the power, we just need, velocity dot the force. But I think we're supposed to assume that all other things being equal, there's the same force of friction that the cyclist is working against. So best case scenario, they're developing that power and with pure efficiency. And 100% of the power they're generating is overcoming the force of friction going down. If that's the case, So the first thing I want to do is I want to figure out I'm thinking I want to figure out the force of friction, but I'm not sure that's what I'm supposed to do here. It's at a constant 4 meters per second, right? So that means that they're not accelerating down the hill. What's that mean? So we could think about the free body diagram. Let me do that just to make sure I'm not getting in trouble here. So you have, bless you, the force of the bike. Force of the bike, right? Let's say it's going parallel down the hill. What else is going on here? You got your normal force, like so. Yeah, you got mg, and of course we have friction force, right? And the friction force and the bike force must be canceling out, but that's not quite the story either, because the gravity is not perpendicular, right? We got to divide the gravity up into the two pieces, right? I call that theta. Remember how it goes? So there's this piece, mg cosine theta, and then there's this piece. Let me make it a different color, actually. There's the blue piece, the mg sine theta, right? And so the situation is that we have the mass times acceleration parallel to the plane is equal to 0 because it's moving at constant speed that's given to us. And that is what? That's giving... so the force of friction, which... good grief. By the way, the normal force is equal to what? Normal force is equal to mg cosine theta, right? Those are balancing out. So that means that the friction force, I'll take down as positive, so we got force of the bike plus mg sine theta minus the force of friction, which is mu. We don't know mu, but we do know the normal force is mg cosine theta, right? Okay, so the force of the bike is equal to mu mg cosine theta minus mg sine theta. I'm not sure quite what to do with that at the moment. I'm going to stop and think about this one. Yeah.
It says the bike coasts down, so I think the force of the bike would be 0.
Oh, wonderful. The bike coasts down. So the force of the bike is 0. Thank you. That just made this problem much, much easier. Thank you. See, words mean things, and we should read them. Thank you. Oh, my goodness, what a relief. What a relief. All right. So, hey, they didn't need to tell us mass, jerks. So mu mg cosine theta equals to mg sine theta. You can cancel the masses, like so. And so we get that mu is equal to what? Mu is equal to, oh, the g's cancel too. So mu is actually equal to tangent theta. Divide by cosine theta, you get mu is equal to sine over cosine, which is tangent. Tangent of 6 is 0.1051. All right, great. Now that still doesn't answer the question to the other part just yet. So what was the question to the other part? What is the... All right, so now I understand the coasting down. What must the cyclist power output be to climb the hill at the same speed? Okay, okay. So the analysis we went through and I just set to 0 actually makes, it's actually necessary on the other side, right? So we can draw the free body diagram going up the hill the other side. I'll do it over here. It's going to be very similar to what we just went through, right? You got the force of the bike. You've got friction force, right? You've still got the normal force. You've got, mg cosine theta this way, and you've got mg sine theta that way, right? If I draw gravity again, gravity looks like this. It's got the this piece and this piece. This is supposed to be a right angle. I fail. Imagine a right angle here. Anyway, so the blue is mg. The gravity's going down the hill there. Okay, great. That part of it's going down the hill. All right, so what we got? We have that and it's still going up at a constant speed, right? So the force of the bike, although I start to feel like this is exactly the wrong way to do it. the force of the bike is equal to the force of friction plus mg sine theta, right? So the force of the bike is actually equal to mu mg cosine theta plus mg sine theta. I think there's an easier way to do this. I start to have a sense that there's an easier way to do this, which I will discover at the end of this analysis and then regret my life. All right. Now, because at the moment I'm not using energy methods hardly at all, which is a warning sign that I'm not doing it the right way, right? But there you go, that's the force of the bike. Now we know mu, and okay, so that's the force of the bike that's necessary, and now we can figure out what the power, the question is what? What's the power output? Oh, well that's easy. So this is, you know, so that's the power, I mean that's the force that we're asking what the power is of. How do you calculate power due to a force? Yeah, force times velocity, assuming that the force is in the same direction in which the motion is. And that's the case here, right? The force of the bike is up the hill, and that's the speed, 4 meters per second. So we should be able to just say that the power developed by the bike is just equal to the force of the bike times 4 meters per second. But we know everything here, so we can figure that out, right? So we've got, I erased it, 0.105, what was it? 0.1051, yeah, 0.1051, that's the mu. This is actually what? This is actually mg times mu. This can be rewritten as mg times mu cosine theta plus sine theta, yeah? So we have 0.1051 times my mass times g, which my mass was 75 kilograms. Oh, we did need to know it, didn't we? 75 kilograms times 9.8 meters per second squared. That's my m, that's my g. Now I got to put in my, oh, I'm an idiot. Fine, cosine 6. And then plus 75. I was trying to avoid doing this twice. It's too late. 75 times 9.8 meters per second squared times the sine of 6 degrees. And all of that times what? Times 4 meters per second, right? All right. I got 614.6. Okay. Good. I guess they won't have to take back my physics degree now. That's good. All right. So 614.6, and this is joules per second. What's that? That's right. It's a what? I mean a watt. See here. Sorry, it was a stupid joke last time. It's still a stupid joke this time, but there you go. 614.6 watts. Questions? Oh, it seems like time for your quiz. Yay! What? You had another homework question? You do now? You know, so like, we have gone from 2 homework problems that were just like nothingness to this. I mean, like, there's no like in-between problem to warm me up for this, right? This this one requires some persistence. Yeah. So here's the parameters on the quiz today. I want you to pick a group of 4 people to work with. All right, so divide yourself up into groups of 4, and then I will give you the quizzes. You will turn in 1 quiz for your group of 4. Now, I have enough quizzes for everyone to look at, but you're going to turn in 1 with all 4 names on it. I give you 1 minute to choose your 4. You 4 are together. There, I chose for you.
Yeah, I have notes.